Okay, ladies and gentlemen, coming up on the board, we're going to talk about a couple of different videos that we had. One was phases of matter. Okay, so we're going to discuss phases of matter, phase diagrams, and the second video was solutions, suspensions, and colloids. So, when we look at our success criteria, or excuse me, our learning target is to identify phase changes that exist in a chemical system. Our success criteria then is to be able to identify condensation, vaporization, freezing, melting, sublimation, and deposition. All of those different parts. Go back here, jumping the gun a little bit. All those different changes in states, we need to be able to identify those. We need to be able to describe the difference between evaporation and boiling, to distinguish between a solute and a solvent, and identify the differences between suspensions and colloids. As we look at these phases of matter, we know that we have liquid, we have solid, we have gas. So we are dealing with right here water. So the solid state is ice, the liquid is just plain water, and the gas is water vapor. So as we go from phase to phase, we have different names for these particular changes. So if we look, this is really pretty easy, okay, melting and freezing, okay. As we go from a liquid to a solid, we call that freezing, the freezing point. As we go from a solid to a liquid, we call that melting, the melting point. Pretty common to us. A little less common when we go from a liquid to a gas, it is vaporization. And when we go from a gas to a liquid, it is condensation. All right? You ever had on that hot summer day, you got a nice big glass of ice water, and all of a sudden the outside of your ice water is wet? Sometimes we call that sweating. The glass is sweating. Well, that is condensation occurring. The water vapor from the air is condensing back into a liquid. Now, these last ones, the last two, from a solid to a gas and a gas to a solid, are a little less common to us. When I look at these, from a solid to a gas is sublimation. So what's happening is we're just actually flying right through the liquid stage. There's such a vast difference in the temperature. Have you ever seen dry ice? When you set the dry ice out, it just looks like it's smoking. Okay? That's that sublimation there. And the last one, going from a gas to a liquid, is deposition. And I'll show you some examples of that here in a little bit. Like right now, okay? Look at this guy right here, okay? Right here. That's a buffalo. That buffalo has had water vapor that has turned into the deposition part, and it is frozen in his fur. I don't know if you've ever done this before. I've done this outside. When it gets really, really cold, okay? When it gets really, really cold, well, I guess actually not this deposition here so much to speak, but I've done it with water, where you take water outside, you throw it up in the air, and it freezes before it lands. Okay, that's not deposition, but that's kind of what that looks like to me. All right, so some different examples. Now we know, as we are looking at this, we talked yesterday about those 5 different quadrants on how do we calculate energy changes at phase changes. Well, where are the actual phase changes occurring? Well, those are occurring here where we got this line right here, that flat line, and right here our other flat line. Okay, so when we have a phase change, for this particular one, it's water. We know that at 0 degrees Celsius, we're going to have a change from ice to water. We know at 100 degrees Celsius, we're going to have a change from water to water vapor. And notice when we have those changes, those flat lines, we are not increasing the temperature. We're not increasing the temperature. That energy is being absorbed so that we can change the different phase. Boiling. We've all boiled water before, right? Whether you're making ramen noodles, you're making mac and cheese, probably boiled water at one time or the other. My wife did yesterday because she made hard-boiled eggs. So we got some boiling of water. Now, when we're looking at boiling, consider the vapor pressures of water at various temperatures. So if we look at this, it might be hard to read if you're in the back. At 100 degrees, 0 degrees Celsius, the pressure in millimeters of mercury, 4.6. 20 degrees Celsius, 17.5. 40 degrees Celsius, 55.3, so-and-so, so-and-so. If you get to 100 degrees Celsius, the pressure is 760 millimeters of mercury. Okay, so as the temperature rises, so does the vapor pressure. We call that, remember, we call that directly proportional. As one goes up, the other one also goes up. Now, what is special about the vapor pressure of water when it reaches 100 degrees Celsius? Gavin? Yeah, that's 760. Remember, 760 millimeters of mercury. Okay? Let's not say so much standard, not say STP, because what's standard temperature? Is it 100? No. So basically, what we're saying here is when we reach 100 degrees, the vapor pressure is standard pressure, which is 760 millimeters mercury, 1 atmosphere of pressure. So that is what is special about the vapor pressure of water. Okay? Same 760 millimeters of mercury is the same pressure as the Earth's atmospheric pressure at sea level. So at sea level, water boils at 100 degrees Celsius. Now, what is happening as the water is being heated? Well, let's look at this, okay? The atmosphere, if we're at sea level, is pushing down on the surface of the liquid of the container. It's pushing down at 760 millimeters of mercury. As we heat the liquid, the temperature climbs, temperature rises. What happens to the vapor pressure? It also goes up. Remember, it's directly proportional. So, at 20 degrees Celsius, we see 17.5. 40 degrees, we're up to 55.3. 149 at 60. 355 at 80. Finally, when we get to 100, it's at 760 millimeters of mercury. So, if the atmosphere is pushing down on the surface of the liquid at 760, the liquid is also pushing up at 760. Okay? When those are equal, the liquid begins to boil. Bubbles rapidly form throughout the liquid as the molecules are at the highest energy, and they are converted to steam. Now, can the boiling temperature of water be changed? What do you think? Yeah, how? Ethan? Yeah, based on the atmospheric pressure. If the atmospheric pressure is not 760, we said it's 760 millimeters of mercury at sea level, right? Is everything at sea level? No. Right here, we can see that we're not at sea level. Our elevation is 876 feet above sea level. So nature already does this. It changes the boiling temperature by what we were just talking about. Here at Saline, Ohio, this elevation here is a little bit different. Maybe our elevation's changed over the years when I made this particular PowerPoint. It's pretty close though. Says the elevation is 892 feet. Water in Seatown boils at 99.1 degrees Celsius. So not quite 100 degrees Celsius. Denver, Colorado. Okay? Denver, Colorado has a much higher elevation. It's down there in the Rocky Mountains. Its elevation is 5,435 feet. So in Denver, Colorado, that water will boil at 94.5 degrees Celsius. Now look right here in this picture right here. Can you see? Right here is the sea, right? Some kind of water right there. So do you think that's at sea level? Yeah. As we come up, here's the city. It's a little bit higher elevation, right? So the boiling's going to be a little bit lower there, the boiling point. Look at this mountain back in the background. The boiling point's going to be even lower in the mountain area, right? So this is Mount Rainier, Washington. The elevation is 14,411 feet, and the water boils at 85.3 degrees Celsius. So right here, if I'm up at the top of the mountain, I'm getting my water to boil at 85.3. If you're down here right by the ocean there, if you're right by the ocean there, it might be a bay, you're going to get your water to boil pretty close to 100. So there's pretty drastic. That's about 15 degrees Celsius difference just by that elevation. Tacoma, Washington, it's that city. Now, if you look at this, here is a phase diagram, okay? A phase diagram. And if you look at the different lines there, we see ice. We see ice right here. And then there's a line between ice and water. Once we cross that line, that's going from freezing to boiling. We know water to water vapor over here. Okay, we talked about that line, vaporization and condensation. Finally, down here, can't we go directly from ice to water vapor? Absolutely. That's my deposition and my sublimation. And something also to look at is the triple point. Okay, the triple point. The triple point of a substance is the temperature and pressure at which a gas, a liquid, and solid coexist in thermodynamic equilibrium. Okay? Now look how small this pressure is. 0.006 atmospheres of pressure. Look at this temperature, 0.01 degrees Celsius. Do you think it'd be real easy to keep that pressure and that temperature right there? Okay? I don't think it would be very easy either. So that would be very, very tough to hit that triple point where we have something existing as a solid, liquid, and a gas. Now let's move on a little bit about solutions. Okay, solutions. Parts of a solution. A solute is the substance that is being dissolved in a solution. A solvent is the medium that is doing the dissolving. So, our most common one, what we call the universal solvent. The universal solvent is what we call water. So, water has many, many, many different things that can be dissolved in it. Can anybody think of something that they've dissolved in water before? What do you think, Devin? Cotton candy. You've dissolved cotton candy in water?
Not completely personally, I just know that you can do it.
Give it a little extra taste. Okay, a little cotton candy taste. Carter, what about you? You dissolved anything in water before? Salt? Salt water? Yeah. Doesn't it call when you're making macaroni and cheese to put a little salt in there? Okay. It used to back in the day. I don't know if it's changed by then. All right. Anybody have the water bottle and put the little packets in the water? Right? Aren't you dissolving that? So, the little packet that you're dumping in there would be the solute. The water in the water bottle would be the solvent. Okay? So we're going to hit on solute and solvent, and we're going to be dealing with that a lot throughout this phases and mixtures unit. A suspension. Okay? A suspension. This is where the particles in the solvent are so large that they settle out of the mixture unless you keep stirring it. The particles are so large that they settle out. So if you look at this picture right here, okay, here is a solution. Do you see any little particles in there? Nope. Okay. Right here, you see the little blue dots. Those are particles right there. Now, these little blue dots will eventually settle down to the bottom, and that is what we call a precipitate. A precipitate. Let me think. Have you ever let your orange juice sit long enough that if you have pulp in it, that all the pulp goes down to the bottom? And then all of a sudden you need to shake it up to mix it back up before you drink it? Okay? That would be an example of that suspension. A colloid. A colloid. These particles are intermediate in size. So it's between a solution and a suspension. The particles are not big enough that you can see them. Okay? They're not big enough that you can see them, but if we do a simple test, you can tell. Now, if you look at these two things, I'm taking a light right here. I've actually not done it, but I found this picture of this light right here. And you can see that right here, you cannot see anything going through there, but do you see that little line right there? See that little line right there? That little line tells me that this solution right here is a colloid. It's got little particles suspended in there, but we can't see them unless we shine that light through there. You can't see the light right there, so that is a solution. Everything is dissolved. They don't have those little particles in there. The next slide right here, is going to be a little bit easier to see. And this whole thing we're talking about is the Tyndall effect. Now, what is the Tyndall effect? It is the scattering of that light. So you see that I've taken this laser pointer, and put it through this liquid, and can you see the direct red line right there? Absolutely. That tells me that that light is bouncing off those colloid particles. So if you shine a light through the liquid, you don't see the light, that's a solution. If you shine that light through there and you see the light, that is a colloid. Any questions for me?